So today we will be talking about IntroSort. So IntroSort is a sorting algorithm that combines both quicksort, heap sort, and insertion sort. Now quicksort's worst case is at oven squared, and it also takes up more space as it sorts, and therefore quicksort has a stack space requirement of O of log n. However, when there are a small number of elements, say about 16 according to some sources, insertion sort is used instead because it's faster and doesn't require as much space. When when the maximum depth is greater than 2 times the log of n of the inputs, then it uses heap sort because heap sort is very low on space usage and not as great as quicksort. So whether it uses quicksort, insertion sort, or heap sort, its worst and best case are all n log n. Since quicksort is not stable, neither will intro sort be stable. Since quicksort also requires all the inputs to be set before starting, it is offline, cannot be updated as it's going. So for this context, we will be using 7 different chips as required, but we will also use an example where there are 16 chips and we use quicksort instead of insertion sort. So we will mix these up. First, let me say that they're ordered from greatest to least. The dealership, not really worth much and practicality, but it's the dealer and the house always wins. So then there's the black, green, blue, red, and white. They all have values associated with them. There may be standards, but let's just assign them the typical points. Okay, so that's called as 1, 5, 10, 25, and 100. And this would just be 1,000. So, oh no, we have scrambled the chips accidentally, and we want to use these in the game, but we have the values in different order. So what do we do? We're going to have to sort them. So in insertion sort, we start by starting at the beginning and placing a separator. Alright, so now we have our marker here, and it's going to separate the sorted list, the sorted section from the unsorted section. So first we're going to look at this. Is the green chip worth more than the black? No, it's not. So we're going to move it to the left of the black chip. Okay. Now the marker has separated the unsorted from the sorted on the left. Now we look at the blue. Is the blue worth more than the black? No, green now, so we move it. Now we look at the red. Is red more than black? No. More than green? No. More than blue though, so we take the red and put it here. Okay, then the dealership, as we have seen before, is worth more than the black chip. Now we have the red chip. This is worth less than the dealer, the black, the green, and it's the same as the red, but we are already at the point where we no longer have to go left anymore, so we just put it in between. Now we have the white, and the white, as we know, is less than all of these, and the blue too. So the best case in insertion sort will be when they're already ordered. So you can see the marker will separate them, and you would just compare the next chip to the one before it and just keep moving down the marker, because it's the next chip is always going to be before the marker. That's just like n. Now the worst case is when it's greatest to smallest, if you want to order it from smallest to greatest. So as you can see here, we want to order it from smallest to greatest, but we have the greatest to smallest already sorted like this. So if we were to put our marker here, we would have to compare the black to this and move the black downwards, and then compare the green one and move it, and then compare it to this dealership and the black ship, and then move it down. And so as we go through the list here, we're going to have to make a comparison to each other marker that we have already sorted before, which is worst case. Okay, so quick sort is a lot harder than the first insertion sort. So as you can see, we have 16 elements here, and we have a pointer at the end, a pointer at the beginning, and one in the middle, which is like for the best average case. So we first see that the first pointer is a black piece, which is worth more than the white piece. So we just change them, we swap the locations of where they are at the same time, but of course code will have you swap one before the other. And next, now we can only swap them because white was both less than blue and black was both greater than blue. In the case, oh, now we move on to green. All right, so now we're on green, and on this side we're on white. So since we know white is less than blue and green is more than blue, we swap them. Yep. Now we have red, but we know that red is worth less than blue. So we leave red where it is and go to black. And on this side, we are at blue, and we know blue and blue are the same value. Yeah, we can see it's the same value. But now here on the left side, we can see the black is worth more than blue, and it's more than blue, so we switch them over. We can do that. Anyways, this proves that in quicksort is not in place, as we can always switch values that was after to before. After doing that, and after getting both markers through the entire array and having them pass each other, and we will then split what we have in half and do the same process on each half, so that we can order the elements, and we keep splitting them in half until we have no more to split. So if we have a lot of elements, we will use heap sort, and I only have missing one. Okay, so I only have 7 here because that's what the requirements were, but this is how it would go. First we build a heap, so we put this up here, then this here, so this will be the parent, left child, right child, left child, right child, left child, and right child. Then we have to organize it so that we have a tree that's balanced and in order. So we create a max heap where the greatest value will be the parent of all the other values. So in this case, we'll have to put the dealer on top, and then switch the green up here, and switch the black over here. So there we have max heap. And then we know that the dealer is worth the most, so we remove this, and then we put like the lowest value on the top, and then we must build a max heap again. So we switch these, and now we know that the top one is the greatest value, so we put the top one outside of it, and we switch it again, and keep doing that, and then we have a sort.